Okay, let's start. So, hello. We're going to continue working through this book. Today or tonight, we are going to continue from chapter 4, which was where we left it since the last video. So, okay, let's see what we learned tonight. So, modules should be deep. One of the most important techniques for managing software complexity is to design systems so that developers only need to face a small fraction of the overall complexity at any given time. This approach is called modular design, and this chapter presents its basic principles. So I don't think that we need a note for modular design. If I'm not wrong, we already have written down this. Yeah, modular design is an approach to fight complexity. It consists in encapsulating and exposing it strategically. So, yeah, encapsulating complexity, modular design. In this chapter presents, yeah, its basic principles. So, let's see. Modular design. In modular design, a software system is decomposed into a collection of modules that are relatively independent. Modules can take many forms, such as classes, subsystems, or services. In an ideal world, each module will be completely independent of the others. A developer could work in any of the modules without knowing anything about any of the other modules. In this world, the complexity of a system would be the complexity of its worst module. Okay, modules can take many forms. So I have a question here because if module can take many forms, classes, subsystems, services, whatever, what is a module? Trying to define that, I think it's important. So perhaps we're going to define that, the author is going to define that in the book, some chapters ahead perhaps, but let's just leave the question here for the record. So what is a module? Unfor- Unfortunately, this ideal is not achievable. Modules must work together by calling each other's functions or methods. As a result, modules must know something about each other. There will be dependencies between the modules. If one module changes, other modules may need to change to match. For example, the arguments for a method create a dependency between the method and any code that invokes the method. Wait. If one module changes, other modules may need to change to match. For example, the arguments for a method create a dependency between the method and any code. Yeah, this is we also took a note about this. It was about the signature of a method being the interface. It was related with that. Or no, we didn't write that, but yeah, I kind of remember. Yeah, I think we could. Yeah, let's continue. So, if the required arguments change, all invocations of the method must be modified to conform to the new signature. Yeah, dependencies can take many other forms, and they can be quite subtle. The goal of modular design is to minimize the dependencies between modules. In order to manage dependencies, we think of each module in two parts. Okay, so let's see the definition. It seems an interface and an implementation. Okay, so we kind of rush with the question, but it's better to play safe and just don't forget that you have some doubts to be answered. So I I would take this node like this. So module, an interface plus a implementation. That is a module. So or what? That is what that is. Those are two parts of a module. So the interface consists of everything that a developer working in a different module must know in order to use the given module. Typically, the interface describes what the module does, but not how it does it. It describes what the module does, but not how. Yeah, so it's like the module. No, no, I got confused. No, no. Let's continue. Typical, the interface describes what the module does, but not how it does it. The implementation consists of the code that carries out the promises made by the interface. Yeah, the promises. It's a interesting way to put it. A developer working in a particular module must understand the interface and implementation of that module, plus the interfaces of any other modules invoked by the given module. A developer should not need to understand the implementations of modules other than the one that he or she is working in. Okay, so it's not like if we are working in a module, we can just simply like not understand not even the implementation of the very own module that we are working on. So at least uh, it's it but it might be a heuristic. It could be should not need should not need to understand. Okay, so it's like an I yeah, let's put it as a statement. Let's put it the operator. I like that word. The operator should not need to know about the details of the implementation of any other module that is not the one they are working on. They are working in. Yeah, these prepositions we always get confused with. Okay. Consider a module that implements balanced trees. The module probably contains sophisticated code for ensuring that the tree remains balanced. However, this complexity is not visible to users of the module. Users see a relatively simple interface for invoking operations to insert, remove, and fetch nodes in the tree. To invoke and insert operation, the caller need only provide the key and value for the new node. The mechanisms for traversing the tree and splitting nodes are not visible in the interface. Okay. For the purposes of this book, a module is any unit of code that has an interface and an implementation. Okay. I'm going to leave it like that because I like to use general definitions. So this can be applied even in other fields, not just software engineering. So I like to think in general terms as this. Like this is like systems thinking. I guess I try to see everything as a system. So a module, it's a good concept to think in systems. So let's leave it in a general way. Okay, each class in an object-oriented programming is a module. Okay, methods within a class or functions in a language that isn't or object-oriented can also be thought as modules. Each of these has an interface and an implementation, and modular design techniques can be applied to them. I like this definition of module. It's very precise. Like it's very binary. You can see this is a module, this is not a module. So higher level subsystems and services are also modules. It makes sense. Yeah, like to interact with a service, you have the famous API, the interface to interact with that. So we have an interface and we have under the hood the implementation. It's a module, a service. But a subsystems, hmm, higher level subsystems and services are also modules. Their interfaces may take different forms, such as kernel calls or HTTP requests. Perhaps this is out of scope of this book. Mm, yeah, I will study about Linux later. I know I will come out with this same question later, so no need to write it down. I know it's ahead in my roadmap of learning, so it's okay. So much of the discussion about modular design in this book focuses on designing classes, but the techniques and concepts apply to other kinds of modules as well. Yeah, this is what I was thinking about. The best modules are those whose interfaces are much simpler than their implementations. Such modules have two advantages. First, a simple interface minimizes the complexity that a module imposes on the rest of the system. Second, if a module is modified in a way that does not change its interface, then no other module will be affected by the modification. If a module's interface is much simpler than its implementation, there will be many aspects of the module that can be changed without affecting other modules. That can be changed without affecting other modules. We should annotate this. No, I think that is it's kind of redundant. Let's continue. So what's in an interface? The interface to a module contains two kinds of information, formal and informal. The formal parts of the interface are specified explicitly in the code, and some of these can be checked for correctness by the programming language. For example, the formal interface for a method is its signature, which includes the names and types of its parameters, the type of its return value, and information about exceptions thrown by the method. Most programming languages ensure that each invocation of a method provides the right number and types of arguments to match its signature. The formal interface for a class consists of the signatures for all of its public methods, plus the names and types of any public variable. I would like to note to write down this. So an interface has two kinds of information. Okay, formal and informal. Each interface also includes informal elements. These are not specified in a way that can be understood or enforced by the programming language. The informal parts of an interface include its high-level behavior, such as the fact that a function deletes the file name by one of its arguments. Yeah, this is, I think I've heard about this. It's like pure functions. It's related. It's this concept of functions that don't have informal elements, informal interfaces. Let's say. So we should write down this such as the fact. I think I will remember this. Yeah, the note is enough. An interface has two kinds of information, formal and informal. Yeah. Where we were at, if there are constraints on the usage of a class, perhaps one method must be called before another. These are also part of the class interface. In general, if a developer needs to know a particular piece of information in order to use a module, then that information is part of the module's interface. Okay, I think I should write down this interface. So this is about the informal parts of an interface. Yeah, any piece of information I need to know before working with a module, it is part of its interface. And in this case, very likely that it will be about the informal interface, but let's leave it like that. So the informal aspects of an interface can only be described using comments, and the programming language cannot ensure that the description is complete or accurate. For most interfaces, the informal aspects are larger and more complex than the formal aspects. Yeah, this is the place where complexity increases more, I believe, the informal interface. One of the benefits of a clearly specified interface is that it indicates exactly what developers need to know in order to use the associated module. This helps to eliminate the unknown unknowns problem described in the previous section. Abstractions. The term abstraction is closely related to the idea of modular design. An abstraction is a simplified view of an entity, which omits unimportant details. An abstraction is a simple view of an entity. Yeah, it's a good definition, abstraction. But I believe, I don't know if I already have this definition here. Module. Yeah, I think um, what notes do I have here? It's a class. Now let's leave this definition here. Abstractions are useful because they make it easier for us to think and manipulate complex things. In modular programming, each module provides an abstraction in form of its interface. The interface presents a simplified view of the module's functionality. The details of the implementation are unimportant from the standpoint of the module's abstraction, so they are omitted from the interface. In the definition of abstraction, the word unimportant is crucial. The more unimportant details that are omitted from an abstraction, the better. However, a detail can only be omitted from an abstraction if it is unimportant. An abstraction can go wrong in two ways. First, it can include details that are not really important. When this happens, it makes the abstraction more complicated than necessary. which increases the cognitive load on developers using the abstraction. The second error is when an abstraction omits details that really are important. Yeah, this is like obscurity, that obscurity thing. This results in obscurity. Developers looking only at the abstraction will not have all the information they need to use the abstraction correctly. Yeah, this is important to write down. An abstraction that omits important details is a false abstraction. It might appear simple, but in reality, it isn't. The key to designing abstractions is to understand what is important and to look for designs that minimize the amount of information that is important. Yeah, this is a really good note to keep. The key the key to design apps abstractions is to understand what is important and to look for designs that minimize the amount of information that is important. Um, Perhaps, yeah, and this again, I have a question that probably will be answered in a moment, but so if the key to design abstractions is to understand what is important, then what is the protocol or heuristics to spot what is important when designing an in an abstraction? When designing, I feel more comfortable putting that question like this because yeah, in this context, I think that this abstraction, this use of the word abstraction is working as a synonym of interface. So I prefer to think about that as abstraction is the process of taking implementation and summarizing, abstracting, and designing the interface. So let's leave it like that. What is the protocol or heuristics to spot what is important when designing an interface? We have a typo. Let's continue. As an example, consider a file system. The abstraction provided by a file system omits many details, such as the mechanism for choosing which blocks on a storage device to use for the data in a given file. Okay. These details are unimportant to users of the file system, as long as the system provides adequate performance. However, some of the details of a file system's implementation are important to users. Most file systems catch this is how do you pronounce that word here? Like catch. Catch. Wait, but it says the noun and the verb is the same? Yeah. So most file systems catch data in main memory, and they may delay writing new data to the storage device in order to improve performance. Some applications, such as databases, need to know exactly when data is written through to storage, so they can ensure that data will be preserved after system crashes. Thus, the rules for flushing data to secondary storage must be visible in the file system's interface. Perhaps it's time to make a drawing for this. The abstraction provided by a file system omits many details. Some applications, such as databases, need to know exactly when data is written through to storage. Yeah, so the implementation should present this in the interface, so they can ensure that data will be preserved after system crashes. Okay, so we depend on abstractions to manage complexity, not just in programming, but pervasively. I think it's pronounced like this, but I don't know what does mean this word. Pervasively, yeah, in a way that exists in all parts or a place or thing. Okay, we depend on abstractions to manage complexity, not just in programming, but pervasively in our everyday lives. A microwave oven contains complex electronics to convert alternating current into microwave radiation and distribute that radiation throughout the cooking cavity. Fortunately, users see a much simpler abstraction consisting of a few buttons to control the timing and intensity of the microwaves. Carbs provide a simple abstraction that allows us to drive them without understanding. This is a good example. So yeah, this is about putting what I mentioned earlier in this part. So this is like in that same style, like showing these concepts in a general way, in a way that applies to any other field. So yeah, cars provide a simple abstraction. So in a cart, we can think of a car as a module because a car has an implementation, which is the motor, and I don't know a lot about cars, but yeah, we can just mention the words here, like electrical motors, battery, power management, anti-lock, brakes, cruise control, and so and so. So this is the implementation. But in order to drive a car, we don't need to know about all this. We just use the cars, the modules interface, which is the wait, what's the word for that? It's I forgot. What's the word for the steering wheel? It's that steering wheel. Yeah. So the interface of a car is the steering wheel, and we could say all these other buttons, and yeah. So we see here the interface of a car, and the implementation is all the other parts of the cart. Yeah, it's a good example. So let's continue. Deep modules. The best modules are those that provide powerful functionality yet have simple interfaces. I use the term deep to describe such modules. Let's write down this. But this is called deep modules provide powerful functionality with simple interfaces. To visualize the notion of depth, imagine that each module is represented by a rectangle, as shown in figure 4.1. Okay, deep modules, shallow modules. The area of each rectangle. A deep module is a good abstraction because only a small fraction of its internal complexity is visible to its user. Module depth is a way of thinking about cost versus benefit. The benefit provided by a module is its functionality. The cost of a module in terms of system complexity is its interface. A module's interface represents the complexity that the module imposes on the rest of the system. The smaller and simpler the interface, the less complexity that it introduces. The best modules are those with the greatest benefit and the least cost. Interfaces are good, but more of or larger interfaces are not necessarily better. The mechanism for file I/O provided by the Unix operating system and its descendants, such as Linux, is a beautiful example of a deep interface. There are only 5 basic system calls for I/O with simple signatures. So, what is the yeah, I kind of struggle to understand this, but wait, let's give it a try. System call. Yeah, in this moment, I'm going to use AI to explain this because I kind of get lost easily with this. But wait, let's give it a try to understand first without aids. Let's see. So yeah, but the issue is that I am not pretty sure what it's a system call. I know it's related with input output, like behavior of a system that produces literally that, like allows you to input information or output information, I guess. So these functions are related with that. But so yeah, there are 5 with simple signatures. Yeah, let's not overcomplicate this. Let's not start yet a study session with AI. So we have, for example, the module open that I guess it opens something obviously, and this means that it returns it returns an int. I believe this is the return value type. Yeah. So we know that this module returns a number, an integer, and receives 1, 2, and 3 parameters, which is a constant type of data type, which this is a like an array of charts, characters, like okay, path, int flags. Okay, let's see what the author is trying to develop here. The open system call takes an hierarchical file name such as and returns an integer file descriptor, which is used to reference the open file. The other arguments for open provide optional information, optional such as whether the file is being opened for reading or writing, whether a new file should be created if there is no existing file, and access permissions for the file if a new file is created. The read and write system calls transfer information between buffer areas in the application's memory and the file. Close ends the access to the file. Most files are accessed sequentially, so that is the default. However, random access can be achieved by invoking the lseek system call to change the current access position. A modern implementation of the unit's I/O interface requires hundreds of thousands of lines, which address complex issues such as how are files represented on disk, how are directories stored. Okay, yeah, there's a lot of stuff that is happening behind this. And all these issues and many more are handled by the Unix file system implementation. They are visible to programmers who invoke the system calls. Implementations of the Unix I/O interface have evolved radically over the years, but the five basic kernel calls have not changed. Another example of these modules is the garbage collector in a language such as Go or Java. This module has no interface at all. It works invisibly behind the scenes to reclaim unused memory. Adding garbage collection to a system actually shrinks its overall interface, since it eliminates the interface for freeing objects. Okay. The implementation of a garbage collector is quite complex, but that complexity is hidden from programmers using the language. Deep modules such as Unix I/O and garbage collectors provide powerful abstractions because they are easy to use, yet they hide significant implementation complexity. Okay, shallow modules. On the other hand, a shallow module is one whose interface is relatively complex in comparison to the functionality that it provides. Yeah, it's the opposite of a deep module. Yeah, and even if a shallow module wouldn't have a complex interface, let's imagine minimal interface and minimal functionality, it might also be wrong in some contexts I think because you can get a gazillion of shallow modules and you are going to you will need to remember all this. So this is like adding complexity. You are adding this about the informal interface. So you have a lot of informal interfaces like many minimal modules that need to call each other in perhaps an order. So yeah, shallow modules. This is the way to not design stuff. It doesn't take wait. For example, a class that implements linked list is shallow. It doesn't take much code to manipulate a linked list. So the linked list abstraction doesn't hide very many details. The complexity of a linked list interface is nearly as great as the complexity of its implementation. Shallow classes are something sometimes unavoidable, but they don't provide help much in managing complexity. Here is an extreme example of a shallow method, taken from a project in a software design class. So this method, private, this means it doesn't return anything. So just starting by this might be a red flag in some contexts, of course, because if we have a function that doesn't provide a sign, a value, anything, it's like a silent function. We execute the function and we don't know um, what happened precisely. Yeah, perhaps it has a high level behavior, but there is not like a precise way. to get an idea of how it went. It might be on that track of thought. So, okay, let's focus. So, this method, it doesn't return anything and it's called add null value for attribute. Okay, it receives a single parameter and it's a string. And what it does, it takes an object and invokes a method of that object, and it puts, okay, yeah, yeah. So why is this a shallow method? If is what we just mentioned, if the interface is simple, so yeah, it's because the high level behavior. So we are affecting another module and we are not even returning any signal about it. Like, in order to check that this module worked correctly, we would need to go to this other object. So yeah, it's starting to make sense, all this about obscurity and informal interfaces. So the informal interface, which by consequence is part of the entire interface of this method, it needs for us to know about this data object and how it works and whatever. So yeah, it's starting to make sense. From the standpoint of managing complexity, this method makes things worse, not better. The method offers no abstraction since all of its functionality is visible through its interface. Yeah, it's like, just wait here. Yeah, it's for doing all this, we could simply just call this method directly. Why bothering in having this entire method, higher parent method for this? It is not simpler to think about the interface than to think about the full implementation. If the method is documented properly, the documentation will be longer than the method's code. It even takes more keystrokes to invoke the method than it will take for a caller to manipulate the data variable directly. The method adds complexity in the form of a new interface for developers to learn. So yeah, just we are adding more informal stuff, informal interface to the operator to remember. So the method adds complexity but provides no compensating benefit. Red flag, shallow module. A shallow module is one whose interface is complicated relative to the functionality it provides. Shallow modules don't help much in the battle against complexity because the benefit they provide, not having to learn about how they work internally. Yeah, I think I would like a note about this. And this might be an insight. Like, the benefit of designing good modules is that is avoiding that we don't need to know the benefit of designing good modules is that we don't need to know about their implementation or when working with them. Classities. Unfortunately, the value of the classes is not widely appreciated today. The conventional wisdom in programming is that classes should be small, not deep. Students are often taught that the most important thing in a class design is to break up larger classes into smaller ones. The same advice is often given about methods. And this might be cause like a misunderstanding about, wait, Cloud is calling or what? He wants a question. Yeah. Wait a moment, buddy. So wait. Uh, the same advice is often given about methods. Any method longer than end lines should be divided into multiple methods. Yeah, I was going to mention, I believe that this might be a misunderstanding or taking this this statement to the extreme level. Because if we assume that the biggest problem in computer science is problem decomposition and we only like focus on that and take it to the extreme, then we are going to end up with class cities. We are going to try to do this, to break up larger clusters into smaller ones as much as possible. So it's not like that to think about problem decomposition, it seems. Yeah, this approach results in large numbers of shallow classes and methods, which add to overall system complexity. The extreme of the classes should be small approach is a syndrome I call classitis, which stems from the mistaken view that classes are good, so more classes are better. In systems suffering from classitis, developers are encouraged to minimize the amount of functionality in each class. If you want more functionality, introduce more classes. Classities may result in classes that are individually simple, but it increases the complexity of the overall system. Small classes don't contribute much functionality, so there have to be a lot of them, each with its own interface. These interfaces accumulate to create tremendous complexity at the system level. Small classes also result in a verbose programming style due to the boilerplate required for each class. Examples: Java and Unix I/O. One of the most visible examples of classities today is the Java class library. The Java language doesn't require lots of small classes, but a culture of classicity seems to have taken root in the Java programming community. For example, to open a file in order to read serialized objects from it, you must create three different objects. So let's read this. Okay, file input stream. So here we are declaring a type of object that is going to contain this variable, which is going to receive its value from this function. Mhm. So yeah, I think the meat of the example is that to open a file, just to open a file, you need to create three different objects just for doing that. Compare that with the examples that we saw about the system calls in Linux. Um, okay, since I am not a very knowledgeable in Java, I think we can take this as understood. Like we got it. Like three different objects just for one action. It smells weird. It's like code smell. Mm, it is particularly annoying and error-prone that buffering must be requested explicitly by creating a separate buffered input stream object. If app developer forgets to create this object, there will be no buffering and I/O will be slow. Perhaps the Java developers will argue that not everyone wants to use buffering for file I/O, so it shouldn't be built on the base mechanism. They might argue that it's better to keep buffering separate so people can choose whether or not to use it, providing choice is good. But interfaces should be designed to make the common case as simple as possible. This is another good statement to write down. So interfaces should be designed to make the common case as simple as possible. Almost every user of file I/O will want buffering, so it should be provided by default. For those few situations where buffering is not desirable, the library can provide a mechanism to disable it. Disable it. Any mechanism for disabling buffering should be cleanly separated in the interface. For example, by providing a different constructor for file input stream, or through a method that disables or replaces the buffering mechanism, so that most developers do not even need to be aware of its existence. In contrast, the designers of the unit system calls made the common case simple. For example, they recognized that sequential I/O is most common, so they made that the default behavior. Random access is still relatively easy to do, using the L6 system call, but a developer doing only sequential access needs to not be aware of that mechanism. If an interface has many features, but most developers only need to be aware of a few of them, the effective complexity of the interface is just the complexity of the commonly used features. The effective complexity of the interface is just the complexity of the commonly used features. Conclusion: by separating the interface of a module from its implementation, we can hide the complexity of the implementation from the rest of the system. Users of a module need only understand the abstraction provided by its interface. The most important issue in designing classes and other modules is to make them deep, so that they can have simple interfaces for the common use cases, yet still provide significant functionality. This maximizes the amount of complexity that is concealed. Um, okay, okay, let's continue with chapter 5: information hiding and leakage. I think it's pronounced like that. Let's see. Leakage. 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 Leakage, yeah. So, chapter 4 argued argued that modules should be deep. This chapter and the next few that follow discuss techniques for creating deep modules. Okay, so we are we're getting into the hands-on or more. I think that we're going to in this chapter we're going to start to notice or to write down a lot of heuristics that will turn into protocol. So it's going to be pretty interesting. The most important technique for achieving deep modules is information hiding. This technique was first described by David Pernas. The basic idea is that each module should encapsulate a few pieces of knowledge, which represent design decisions. The knowledge is embedded in the module's implementation but does not appear in its interface, so it is not visible to other modules. Okay, so the most important technique for achieving the modules is information hiding. See, this is pretty related with our most recent notes. Let's see, interfaces. Yeah, it's let's. I don't know. I'm not going to write this down. Let's wait. It's kind of redundant if I write it right now. The knowledge is embedded in the module's implementation but does not appear in its interface, so it is not visible to other modules. The information hidden within a module usually consists of details about how to implement some mechanism. Here are some examples of information that might be hidden within a module. Okay, wait. The information hidden within a module usually consists of details about how to implement some mechanism. So some examples of information hiding, it could be how to store information in a B tree and how to access it efficiently, how to identify the physical disk block corresponding to each logical block within a file, how to implement the TCP network protocol, how to schedule threads on a multi-core processor, how to parse JSON documents. The hidden information includes data structure and algorithms related to the mechanism. It can also include low-level details such as the size of the page, and it can include high-level concepts that are more abstract, such as an assumption that most files are small. Information hiding reduces the complexity in two ways. First, it simplifies the interface to a module. The interface reflects a simpler, more abstract view of the module's functionality and hides the details. This reduces the cognitive load on developers who use the module. For instance, a developer using a B-tree class need not to worry about the ideal fan-out. Fan-out, what is that word? Fan-out. To spare out. Okay. For instance, a developer no need to worry about the ideal fan-out for nodes in the tree or how to keep the tree balanced. Second, information hiding makes it easier to evolve the system. If a piece of information is hidden, there are no dependencies of that information outside the module containing the information. So a design change related to that information will affect only the one module. For example, if the TCP protocol changes, the protocol's implementation will have to be modified, but no changes should be needed in higher level code that uses TCP to send and receive data. When designing a new module, you should think carefully about what information can be hidden in that module. If you can hide more information, you should also be able to simplify the module's interface, and this makes the module deeper. Note: hiding variables and methods in a class by declaring them private isn't the same thing. Okay, this is worth remembering. Hiding information, hiding in a class by declaring it private is not the same thing as information hiding. And let's switch this word because it's kind of redundant to use it again, like repetitive. So it's better put it this way: hiding data in a class by declaring it private is not the same thing as information hiding. Okay. Private elements can help with information hiding since they make it impossible for the items to be accessed directly from outside the class. However, information about the private items can still be exposed through public methods such as the getter and setter methods. When this happens, the nature and usage of the variables are just as exposed as if the variables were public. The best form of information hiding is when information is totally hidden within a module, so that it is irrelevant and invisible to users of the module. However, partial information hiding also has value. For example, if a particular feature or piece of information is only needed by a few of a class users and it is accessed through separate methods so that it isn't visible in the most common use cases, then that information is mostly hidden. Okay. Information leakage. The opposite of information hiding is information leakage. Information leakage occurs when a design decision. Wait, am I pronouncing right this word? I forgot. Leakage. Leakage. Yeah. Information. This creates a dependency between the modules. Any change to that design decision will require changes to all of the involved modules. If a piece of information is reflected in the interface for a module, then by definition it has been leaked. Okay. If a piece of information is reflected in the interface for a module, okay, let's write down this. But now in this moment, I think it's important remembering this. The most important, yeah, it's yeah, we should write this down. The most important technique for achieving deep modules is information hiding. And I also want to write down this. This could go in heuristics, I believe. If a piece of information if a piece of information is reflected in the interface in a module's interface, then it has been leaked. Thus, simpler interfaces tend to correlate with better information hiding. However, information can be leaked even if it doesn't appear in a module's interface. Suppose two classes both have knowledge of a particular file format. Perhaps one class reads files in that format and the other class writes them. Even if neither class exposes what happened with the okay. I thought I got an incomplete book. So wait, suppose two classes both have knowledge of a particular file format. Yeah, particular file format. Even if neither class exposes. Oh, okay, this is corrupted, I guess. let's let's ignore this and we will come back to this later. But yeah, the idea is that we need to avoid this, but wait, this was going to be important. Information can be leaked even if it doesn't appear. Uh, This needs to be written down. Information can be leaked even if it doesn't appear in a module's interface. Yeah, let's leave a question here. How? Okay, a post request in HTTP protocol consists of text sent over a TCP socket. Each request contains an initial line, a collection of headers, optional body. The initial line contains the request type. Okay. Each header line consists of a name such as content length. Okay. Example, too many classes. The most common mistake made by students was to divide their code into a large number of shallow classes, which led to information leakage between the classes. One team used two different classes for receiving HTTP requests. The first class read the request from the network connection into a string, and the second class parsed the string. This is an example of a temporal decomposition. First we read the request, then we parse it. Information leakage occurred because an HTTP request can't be read without parsing much of the message. Wait, information leakage occurred because an HTTP request can't be read without parsing much of the message. For example, the content-led header specifies the length of the request body, so the headers must be parsed in order to compute the total request length. As a result, both classes needed to understand most of the structure of HTTP requests. Yeah, it's like leaking the implementation information across several modules. I think this is where it's going to. Yeah, this approach also created extra complexity for callers who had to invoke two methods in different classes in a particular order to receive a request. Because the classes share so much information, it would have been better to merge them into a single class that handles both request reading and parsing. This provides better information hiding since it isolates all knowledge of the request format in one class, and it also provides a simpler interface to callers. Okay. Oh, wait, this is a heuristic. So I think we're going to switch this. Information hiding can often be improved by making a class slightly larger. Yeah, this sounds way more like a heuristic than this other one. And take a look at this heuristic. It's very related with information hidden. Isolating complexity in a place where it will never be seen is almost as good as eliminating it. Okay. One reason for doing this is to bring together all of the code related to a particular capability so that the resulting class contains everything related to that capability. A second reason for increasing the size of a class is to raise the level of the interface. For example, rather than having separate methods for each of three steps of a computation, have a single method that performs the entire computation. This can result in a simpler interface. Both of these benefits apply in the example of the previous paragraph. Combining the classes brings together all of the code related to parsing and an HTTP request, and it replaces two externally visible methods with one. Of course, it is possible to take the notion of larger classes too far, such as a single class for the entire application. That sounds crazy. Chapter 9 will discuss conditions under which it makes sense to separate code into multiple smaller classes. Okay, after an HTTP request has been received by a server, the server needs to access some of the information from the request. But I already got this, I believe so. Let's skip the example. We need to kind of hurry up a little bit, because we are still only in 47 page, and the series of these videos it's already I believe more than 3 hours. So yeah, let's just hurry up a little bit. Taking it too far, information hiding only makes sense when the information being hidden is not needed outside its module. If the information is needed outside the module, then you must not hide it. Suppose that the performance of a module is affected by certain configuration parameters, and that different uses of the module will require different settings of the parameters. In this case, it is important that the parameters are exposed in the interface of the module. Okay, this is kind of an obvious conclusion, but should we write this down? Yeah, just in case, let's put a statement. Information hiding will make sense when the information is not needed. And I would like to save this as a heuristic. Your goal should be to minimize, yeah, as a software engineer, my goal should be to minimize the amount of information needed outside a module. Conclusion: information hidden in deep modules are closely related. If a module hides a lot of information, that tends to increase the amount of functionality provided by the module, while also reducing its interface. This makes a module deeper. Conversely, if a module doesn't hide much information, then either it doesn't have much functionality or it has a complex interface. Either way, the module is shallow. When decomposing a system into modules, try not to be influenced by the order in which operations will occur at runtime. This is another heuristics, could be. When decomposing a system into modules, try not to be influenced by the order in which operations will occur at runtime. That would lead you down the path of temporal decomposition. I want to save this as a heuristic, but I feel that to really understand this part, we need to see we need to design an exercise or something. This is going to be something that we are going to ask AI for. So let's save it. When decomposing a system into modules, try not to be influenced. Instead, think about the different pieces of knowledge that are needed to carry out. Yeah, let's just copy and paste of all this. I think it's important that we are keep the precision on this mini protocol. It's why because it gets this format weird. Okay. And let's add a reminder because just copying and pasting this is not going to work if we don't do a serious process of this information. So let's. I still don't get this heuristics. Well, I feel I might need a hands-on exercise like like yeah, like seeing an example of how decompose a system by being influenced by the order of operations at runtime, and then another example hands-on exercise of the recommended approach. Yeah, so this is like the prompt that we are going to send AI later, or it's going to read it automatically. But I find it useful because if we are just going to copy and paste this and we are not specifying why we're doing it or what we are not getting, like I think this context is important because it it's right now we have the idea of what it might work to understand this. So let's not lose that and just store it as a future prompt.